Yes, they already asked. It's fine.
It's okay? Okay.
Yeah, it's fine.
Okay, so you have 25 minutes and then 5 minutes for questions. You can start. Thank you.
Okay. So thanks very much to the organizers for the invitation. I was really excited about coming to Argentina, so it's a shame that we can't be there together, but it's still very nice that the conference is happening. So this is all going to be based on joint work with my colleague Matt Roberts, who's also at Bath, and our joint PhD student Zsofia Taigash. So this talk is going to be about a process called the N-particle branching random walk. And this is a discrete time branching selection system, and it was introduced in the physics literature by Brunet and Derrida in the 1990s. And the process consists of a fixed number, capital N, of particles that have locations on the real line at each integer time step. And we're going to let capital X be a real valued random variable. And we'll refer to this as the jump distribution. And we're going to have some arbitrary initial configuration of the particles on the real line at time 0. And then at each non-negative integer time little n, then each of the n particles is going to have 2 offspring. And so we'll have 2n offspring particles, and each of these particles makes an independent jump along the real line away from its parent's location. And that jump has the same law as the random variable x. And then the n rightmost particles out of those 2n offspring particles form the new population at time n+1. So they form the next generation of the process. So the reason that this is called a branching selection system is that we have first a branching step here, where each particle has 2 offspring and they each make a jump away from the position of their parent. And then we have what's called a selection step, where only n of these 2n offspring particles survive and the other n particles are killed. And you can see this process is a toy model for a population under selection. So you can see the position of a particle on the real line as representing its evolutionary fitness. And then what we're doing in the selection step is we're saying that only the n particles with the highest fitness are surviving, and the n least fit particles are being killed in such a way that the population size is being kept constant and equal to n. So in the pictures on the bottom of the slide, I'm going to try and show you what one time step of this process might look like when we take capital N equal to 4, so when we have 4 particles in the system. So first of all, each of these 4 particles has 2 offspring, each of which makes an independent jump from its parent's location. So these 2 might be the offspring of this particle. And then we see which 4 of those 8 particles are furthest to the right, so these 4, and then these 4 are the 4 leftmost particles. So these 4 particles are going to be killed, and these 4 particles on the right are going to survive to form the next generation of the process. So at time n+1, then the particle configuration might look like this. So another particle configuration of 4 particles on the real line. So you can see that a particle in this generation could end up having no offspring in the next generation after the selection step, like this particle here, or it could have exactly 1 offspring, like these 2 particles, or it could have 2 offspring. And some notations, I'm going to write x1n of little n up to xnn of little n for the ordered particle positions at time little n. So I'll sometimes call x1n of n the leftmost particle position, and this is the rightmost particle position. So there are sort of 2 main things that we're interested in for the behavior of this process. So the first is the asymptotic speed at which the cloud of particles moves to the right on the real line. And the second is the genealogy or family tree of a sample of particles from the system. So first of all, I want to tell you about what's known and conjectured when the jump distribution is light-tailed. So first of all, for the asymptotic speeds, so let's suppose that capital X, which was the jump distribution, has a finite mean. In that case, there exists a deterministic speed Vn that's strictly positive and finite, such that if we take the position of the rightmost particle at time little n and divide it by little n, that converges almost surely and in L1 as time little n goes to infinity to this Vn. And we also get the same thing if we take the leftmost particle position rather than the rightmost. So this can be proved using Kingman's subadditive ergodic theorem. So a proof of this appears in the paper by this paper by Bérard and P. But what Bérard and P also proved in 2010 is some fine asymptotics on the behavior of V capital N as capital N goes to infinity. So this is the asymptotics for the asymptotic speed as the number of particles in the system goes to infinity. So what they showed is that if the jump distribution has a finite exponential moment and a couple more technical assumptions on the jump distribution, then if you take capital N to infinity, then the limit of V capital N exists. So let's call it V infinity. And they also showed that if you take V infinity minus V capital N, then that goes like some positive constant C times log n to the minus 2 as capital N goes to infinity. So this is saying that the asymptotic speed converges to a constant, but it converges extremely slowly because capital N needs to be extremely big for log n to the minus 2 to be very small. And this was first conjectured by Brunet and Derrida in 97, and there's a related result for the Fisher KPP equation with noise that was proved by Miller, Mitnick, and Castell in 2009. So that's what happens for what the asymptotic speed of the cloud of particles is in this light tail case. So then what happens with the genealogy? So what do I mean by the genealogy? Well, I mean that we would fix an integer k, and we would take the total number of particles in the population, capital N, to be extremely large. And we sample k particles uniformly at random from the capital N particles at a large time and trace their ancestry backwards in time. So then we get a coalescent process in which ancestral lineages coalesce or merge when they have a common ancestor. And it's conjectured, so this is due to Brunet, Derrida, Müller, and Meunier, that if the jump distribution X is light-tailed, then the genealogy of a sample on a log n cubed timescale converges to a coalescent called the Bolthausen-Snitmine coalescent as n goes to infinity. So that's what's known and conjectured in the light-tailed jump distribution case. But for the rest of the talk, I want to talk about the case where the jump distribution is heavy-tailed, and in that case, the properties of these two types of behaviour are rather different. So what do I mean by a heavy-tailed jump distribution? So on this slide, just for concreteness, I'm going to take a positive constant alpha and suppose that the probability that our random variable capital X is bigger than X goes like X to the minus alpha as X goes to infinity. So we'll make this assumption a bit weaker later on, but this is maybe a bit easier for this slide. So first of all, what happens with the asymptotic speed? So this is a result of Bérard and Maillard from 2014. So they showed, first of all, if the jump distribution has finite mean, then if we take the asymptotic speed, so if we take the position of the rightmost particle at time little n, divide by n, little n, and take little n to infinity, so we saw on the previous slide that limit exists almost surely in L1, so it's some V capital N. But Bérard and Maillard showed that the asymptotics for V capital N as n goes to infinity, so they showed that it goes like a constant that depends on alpha times n to the 1 over alpha, and then times log n to the 1 over alpha minus 1. So in particular, because this term kills this term, as n goes to infinity, then this asymptotic speed goes to infinity. So the asymptotic speed at which the cloud of particles moves to the right gets extremely large when the total number of particles is extremely large. And they also characterize the behavior when the jump distribution has infinite mean, and in that case, there isn't an asymptotic speed and the cloud of particles accelerates. And they actually proved these results under slightly weaker assumptions than this one that I've got here, but I was just trying to give you a nice simple form of this Vn asymptotic. And then for the genealogy, what Bérard and Maillard conjectured is that the genealogy of a sample of particles on a log n timescale is approximately given by a star-shaped coalescent when capital N is large. So this is a different timescale to what's conjectured in the light-tailed case, where the timescale is conjectured to be log n cubed. So here it's conjectured to be log n, and they're saying that it should be a star-shaped coalescent. So what I mean by that is a coalescent in which all the lineages don't coalesce until a single time, where all the lineages simultaneously coalesce into a single lineage. And our main result is essentially a proof of this conjecture. So before I show you our main result, I want to give some more precise assumptions about the jump distribution for our main result. So let's define a function h such that the probability that our random variable capital X is bigger than little x is given by 1 over h of x for non-negative x. And we're now going to assume that h is regularly varying with some positive index alpha. So what I mean by that is that for any positive y, if you take h of x times y and divide by h of x, then that converges to y to the alpha as x goes to infinity. So a good example to keep in mind would be that we could take h of x to be equal to x to the alpha for x greater than or equal to 1. And the other assumption that we're going to make is that x is non-negative almost surely. So what this means is that all of the jumps that are made by offspring away from their parent are non-negative. And this assumption is sort of expected to not make any large difference to the overall behaviour. And this assumption was also made by Bérard and Bérard and Maillard in their work, but it does make quite a few things simpler in the proofs. And then just a bit about the time scale and the space scale that we're going to end up looking at the process on. So we're going to define ln to be the ceiling function of log base 2 of n. So this turns out to be a relevant timescale for the process. And one way to see that this might be a relevant timescale is that a particle can have 2 offspring in the next generation if neither of them are killed, if neither of its 2 initial offspring are killed in the selection step. So because 2 to the power of ln is at least n, that means that in a time ln, it's possible for a particle to grow n descendants. And so it's possible for a single particle's descendants to take over the whole population if none of them are killed in selection steps before they've taken over the population. And then it turns out that the relevant space scale to look at the process on is this value an, which is h inverse of 2n times ln. And by h inverse, I mean the generalized inverse, so h inverse of x is the infimum of y such that h of y is bigger than x. And one way to see that this might be the right space scale is, so let's take 2 positive constants, c1 and c2. So how many, what's the expected number of jumps of offspring away from their parents of size bigger than c1 times an in a time interval of length c2 times ln? Well, at each time step, we have 2n jumps because there are 2n new offspring. And then we're saying that there are c2 times ln time steps. And then to get the expected number of jumps that are bigger than c1 an, we just need to multiply by the probability that a single jump is bigger than c1 an. And then by the definition of h up here, we can just write this as 1 over h of c1 an. And then because h is regularly varying, if we let n go to infinity, we can put this c1 at the front here and put it to the power of alpha. So we'll have c1 to the alpha times h of an. And by the definition of an here, h of an is going to be roughly 2n times ln as n goes to infinity. So we can write this thing on the bottom here as roughly c1 to the alpha times 2n ln. But now we can cancel the 2n ln from the top and the bottom, and we get C2 over C1 to the alpha. So in particular, this is saying that as n goes to infinity, the expected number of jumps of size bigger than C1an in this time interval is going to be constant. So we should have order of 1 jumps of this size. So perhaps this is a relevant space scale to look at the process on, and this turns out to be the case. So now I'm going to show you our main result. So I'm going to show you a sort of slightly wordy version of the result. So when I say with high probability, what I'm meaning is with probability that can be taken arbitrarily close to 1 by taking capital N, the total number of particles, to be large enough. So what we prove is, so let's take a small positive eta and an integer k and a time t that's bigger than 4 ln. Then we can say that the following occurs with high probability. So first of all, we can say something about the spatial distribution of the cloud of particles. So we can say that at this time t, there are n minus little o of n particles, so almost all the particles are in this space interval, x1n of t up to x1n of t plus eta times an. So almost all of the particles are in this interval starting at the leftmost particle, so they're within distance eta an of the leftmost particle. So on the an space scale, they're very close to the leftmost particle. And then the other thing that we prove is about the genealogy. So we say that the genealogy on an ln timescale is asymptotically given by a star-shaped coalescent. So more precisely, what we say is that there exists a random time capital T that's between little t minus 2 ln and t minus ln, such that if we take a uniform sample of k particles out of the n particles at time t, then with high probability, every one of those k particles is descended from the rightmost particle in the system at time capital T, but also no pair of particles in the sample has a common ancestor after time t plus epsilon n times ln, where we've chosen a sequence epsilon n, which goes to 0 as n goes to infinity, but such that epsilon n times ln goes to infinity as n goes to infinity. So this is saying that if you go back to time capital T, then all of the ancestral lineages in the sample have coalesced. But if you go only back to time capital T plus something that's very large but can be much smaller than ln, then no pair of ancestral lineages from the sample has coalesced. So on the next slide, I'm going to show you a picture to sort of try and illustrate this genealogy result. So I'm just going to copy over these 4 lines at the bottom onto the next slide below the picture. So this picture is showing the case where we sample k equals 6 particles at time t. We trace their ancestry backwards in time, and there's a time capital T where all of the particles have coalesced. They've got a single common ancestor. And the time little t minus capital T is between ln and 2 ln. And then there's this time t plus epsilon n ln that's little o of ln away from capital T. So these dots are here because the time scale of this is much, much bigger than this amount of time. And so you can see that between this time and this time, so here none of the lineages have coalesced, and between these times they just coalesce pairwise. So there's only ever 2 lineages that merge together into one, and that's because in our process, then each individual only ever has at most 2 offspring in the next generation, and lineages can only merge when they're both offspring of the same parent. So we can only ever have pairwise mergers, but it's just that all of these pairwise mergers are happening over a much shorter timescale than the overall timescale for coalescence. And so when we look at this coalescent process on the timescale of coalescence, then it looks like it's star-shaped coalescent. It looks like these 6 lineages have all instantaneously merged together. So that was our main result. Then I just want to talk about a couple of other results that sort of put our main result in context a little bit. So here I'm reminding you of what our spatial distribution result said. So it said that at a time t, then n minus little o of n of the particles are within distance eta times an of the leftmost particle, where eta can be an arbitrarily small positive constant, and that's with high probability. So I said that an should be a relevant timescale for the process because there will be order of one jumps of a size order an on a ln timescale. But it turns out that it's also the relevant process for the relevant space scale for the particle system, in the sense that the diameter of the cloud of particles has size of order an. So what we can show is that there exist PR and QR between 0 and 1, such that QR goes to 0 as R goes to infinity, and PR goes to 1 as R goes to infinity. And for any positive R, if the number of particles n is large enough, and if we take a time t bigger than 3 ln, then the probability that the difference between the position of the rightmost particle at time t and the position of the leftmost particle at time t is at least R times an. That's between PR and QR. So what does this mean? Well, it means that if we take R to be really, really small, then PR is going to be very close to 1. So this is saying that the probability that the difference between the rightmost and leftmost particle positions, or the probability that the diameter at time t is at least this little r times an, is going to be very close to 1. So it's unlikely that the diameter is very, very small on an an space scale. But if we take R to be really big, then QR will be really small. And so this probability will be very small. So it's saying the probability that the diameter is really big on an an space scale is very small. So the diameter is of order an, but almost all of the particles are very close to the leftmost particle on this an space scale. And then there are just a few outliers that are further away. And then, so this is reminding you of our results about the genealogy. So I said that with high probability, there's a time capital T between little t minus 2 ln and t minus ln, such that if we take a uniform sample, then with high probability, all of the particles in the sample are descended from a single particle at time capital T, but no pair has coalesced a bit after that time capital T. But what we can also show is that if you take an interval inside this interval that has of size of length of order ln, then there's a positive probability that capital T is in that smaller interval. So we can say that if you take S1 strictly less than S2 between 0 and 1, then there's a positive P that depends on S1 and S2, such that if the number of particles n is large enough, and if you take a t bigger than 4 ln, then the probability that capital T is between t minus 2 ln plus S1 ln and t minus 2 ln plus S2 ln is bigger than P. So what I really mean here is sort of shorthand for saying the probability that there exists a time capital T in this time interval such that this thing happens, so such that all the particles coalesce by that time, but not no coalescence happens before that time. So am I essentially out of time? I think you said 25 minutes. Oh, you're muted.
Yeah, you have 30 minutes.
Yeah, I thought it was 30 minutes. Okay.
Yeah.
But someone said 25. Okay, fine. So I guess I've got a few minutes to say a little bit about heuristics for the proof. So I'm going to try and explain what's going on in this picture. So I'm going to let T1 be T minus ln, and C is going to be a small positive constant. And then let's let capital T be the last time before time T1 when a particle makes, an offspring particle makes a jump that's of size bigger than this constant C times an away from its parent, and also takes the lead in the sense that it becomes the new rightmost particle. So I'm going to try and show in this picture what will then happen between time capital T and time little t. So time is going up the screen, So first of all, at time capital T, what this picture is with the letter A is trying to show is that we've got all our particles here, and then there's this single particle that's taking the lead by making a big jump. So what's happening at A is that a particle makes a big jump at time capital T and it takes the lead. And it's likely that it takes the lead by a distance of order AN. And then actually its descendants are going to stay in the lead until time T1. And the reason for that is that, so first of all, by the definition of the time capital T, because it's the last time when a particle takes the lead with a big jump before time T1, then other particles can't take the lead with a big jump between times capital T and T1. But also because the jump distribution is heavy-tailed, that means that if a particle wants to get ahead of this leader particle at time capital T, it's got to move order of AN, but it's very hard for a particle to move order AN without making at least one jump that's bigger than this small constant times AN because of the heavy-tailed jump distribution. So it's unlikely that anyone actually beats the descendants of this particle until time T1. But after time T1, there could be other big jumps that get ahead of the tribe descended from this leader particle. So that's what B is showing. So this would be a particle that's making a big jump and getting ahead. But we said that there are only order 1 jumps in a time interval of length Ln, like this time interval, which are of order AN. So there are only going to be order of 1 big jumps in this time interval. And also it's likely that none of these big jumps are going to be very soon after the time T1. And so they all have time significantly less than Ln to build a tribe of descendants. And your tribe of descendants can at most double at each time step. And so because 2 to the Ln is roughly n, then because they've got significantly less time than Ln, they're each going to have little o of n descendants at time t. And because there are only order 1 of them, then by time t, there are only going to be little o of n of particles descended from big jumps that got ahead of this tribe. And for the same reason as I said before, it's very difficult for particles to get ahead of this tribe without making a big jump that goes past the tribe. So essentially, only little o of n of particles are going to get ahead of this tribe by time t. So what happens inside this tribe? Well, so C is trying to show you a sort of zoom in of what happens early on. So initially, the tribe descended from the time this particle, the time t leader. Initially, it just doubles in size at each time step because there are only a few particles ahead of it, and so none of the particles descended from this particle are killed at the selection steps. And this keeps going until this tribe has almost size capital N. And then and that happens at time roughly t plus ln, capital T plus ln. And then what happens at that time is shown in D. So on the time interval t plus ln up to t, then this leader tribe can't grow in size anymore. So I'm sort of showing you in this picture here that some of the offspring are going to be killed from now on in selection steps. But because we said that there are only going to be little o of n particles ahead of this tribe, it's still going to have size capital N minus little o of n by time little t. So that means that at time little t, almost all the particles are in this tribe descended from this single particle. And it's not too hard to use that to show that most of these particles are quite close together on the AN timescale, which is what space scale, which is what we wanted. And then, so there are some other things to show, which I'm not going to tell you about, but essentially, then it boils down to showing that there is such a time capital T between times t minus 2 ln and t minus ln. And then also we have to show that that the coalescence is star-shaped in the sense that I said. But hopefully that gives you a little bit of a picture of what the heuristics for the proof look like and what happens in the process between times capital T and little t. So I think that's my 30 minutes. So thank you very much for your attention.
Thank you, Sarah, for very nice talk. Is there any question or comment?
May I ask a question?
Yes.
So I was wondering if instead of considering this discrete time process, you consider the continuous time version.
Mm-hmm.
Do you expect to have the same behavior, or the behavior is going to be different from this star-shaped coalescent that you just described?
So you mean that each particle would branch after an exponential time and then make a jump?
Yeah, exactly.
Yeah. Yeah, I would expect so. I mean, it would just, because then sort of the trajectories of particles would just be continuous time random walks, but still with the heavy-tailed. I mean, it's the heavy-tailed nature that really ends up with this star-shaped coalescent, because it means that there's sort of one really big jump that ends up, that particle ends up taking over the whole population, and I think you would get the same behavior. So I mean, people study the N-particle branching Brownian motion has been quite well studied, but of course that doesn't have the heavy-tailed nature to it. But I'm not sure anyone's looked at a sort of continuous time version of the N-particle branching random walk with heavy tails, but I think it would have the same kind of behavior.
Okay, thank you.
No problem.
Any other question?
I don't have a question, but I want to make a comment, Sarah. It's very nice. I mean, I really like this, what you did there with this heavy-tailed things, and I really like this star-shaped genealogy. I mean, that's a really cute result. So, that's just wonderful.
Thank you.
Any other question?
I have a question. So also very nice talk, Sarah. I was wondering if it's expected to find something like intermediate, like some critical behavior between the star-shaped and the Smith-Van-Rookhausen. Yeah, I guess.
Yeah. So that's a very good question. In fact, yeah, I sort of didn't have time to crowbar that in, but that's actually something that my PhD student Sophia is working on at the moment. So we're looking at what happens if you have a stretched exponential tail rather than something light-tailed or heavy-tailed. And so this is very much work in progress, but we think that you still get this log n timescale for the coalescence until some critical value of so your stretched exponential tail is like e to the minus x to some power, and we think that there's some critical value of the power at which the coalescence time changes behavior, but we're not really sure yet. But she's done some nice simulations as well, which are quite fun, but I didn't have time to fit them in.
Okay, thank you.
Is there any other question? Okay. Thank you very much, Sarah. I like it a lot, your talk. So we now have, we start immediately the next talk. Manuel?
I think we wait until 10:40, right?
Okay, so we have a 4 minutes break. So.
Should we try the sharing screen thing?
Yeah, so better try to set the thing in the meanwhile.
Okay, so it doesn't work. Interesting. Let's try again. Oh, that's the wrong thing. I didn't want to do that. That's always sharing the wrong thing. I don't understand. It's very funny because it doesn't share what I want to. Ah, now it comes. Okay. So it seems to be much better.
So Anton, are you in Bonn right now?
I'm absolutely in Bonn, yes. That's well, I can make myself go somewhere else, but that would not really help. And now I'm in my office as usual. I mean, I thought I would go to Buenos Aires, but you know.
But
But I bought a steak for tonight, so I mean, to get some feeling of, maybe I have a bottle of Malbec or something.
yeah. Okay, Anton, so you agree in being recorded, right?
Yeah, I agree. I mean, I'm constantly being recorded for my students, so it's quite used to be recorded.
Okay, so we can start the recording.
So I think we can start now, right?